Hi everyone, I'd like to present FootMaps. So this is done by me, Leanna, and Brandon. So firstly, I'll be covering the solution demonstration. Then Leanna will be covering the IoT structure and UML diagrams. And lastly, Brandon will be covering the security measures. Now I'll be going through the features that we've implemented for the FootMaps application. So on the right, I have two emulators that are open. So one will show the user logged into FootMaps, how the process goes, what data is collected from the user. And another emulator will be used to show what the admin sees, the decisions that the admin will make based on the data that is collected from the user. So for the user, first they will have to sign up for a new account. So in this case, maybe it's George. So the sign in and sign up is handled by the Realm database. So upon successful sign up, it will be redirected to this login page. So I've set up the permissions to allow for both audio and locations already to save us some time. And I'll focus on what inputs are being collected by George after he logs into the application. So you can see just now we had a notification that opened up. So I'll be touching on what that is and what function it has first. So over here, when I slide down, you can see that over here it's asking us how crowded will fire entrance B is. Oh, so now it's changed. So now it's asking us how crowded Brisbane Voucher Street 66 is. So for now, I'll just put little crowded first. But what that notification is trying to simulate is that at this point, we could be walking past Brisbane Voucher Street 66. And because we are near to this beacon, we will receive a notification to input on how crowded that area is. So now we have another notification for River Fire Entrance A. So in this case, maybe I'm walking past River Fire Entrance A and I don't think it's very crowded, so I'll put no crowd over there. So let's say I'm in the middle of navigating. So in this case, this is the navigation feature of the application. So you can see that the start location is automatically filled. This is because it's filled based on our current location. So over here on the left, we are at Coast West End. So let's say I want to go to QT Gardens Point. So over here, you can see that we are recommended 3 different routes based on how crowded they are. And over here, I'll just select heavily crowded. And I'm given directions to my destination based on the crowd levels. So ideally, if we go back, these crowd levels, the data is based on the beacon data that we've collected, as well as the data that the user has inputted in. So maybe just now when I inputted River Fire Entrance A is crowded, and if that somehow is a point along the route, then maybe it will cause the route to be more heavily crowded when it's displayed over here. So now I'll move on to how the admin would view the data that we collected from here, as well as the decisions that the admin will make based on what data is collected. So another thing to note is, other than the user input through the notifications, there is also audio data and accelerometer data being collected here. But I would show that in conjunction with the admin view. So let me just shift over to the admin view over here. So if I refresh the results here, you can see that the crowd levels have changed based on the input that we have made from the user application. So just now, Brisbane Voucher Street 66 was very crowded, but because just now when we were asked how crowded it was, we put it was little crowded. So the crowd level reduced from being a large crowd to now it's in between little crowd and large crowd. So basically, what this is trying to do is at a glance tell the admin what is the rough crowd level. So how this is calculated is that it aggregates the data based on the past hour and provides that to the admin. So the crowd level is as recent as possible. So if I click into Brisbane Voucher Street 66, I'll be able to get more information as an admin on the history of the crowds in the area. So over here, I can see that on the 4th of November, there was like a spike in the crowd. So maybe that would contribute to my decision making when I'm deciding whether or not, oh, is this increase in crowd unnatural? Is it because of a special event? And that might impact my decision on whether I want to contact the authorities. So more information we can see here is that because this is just crowd level in the past 12 hours, the user might want to, or in this case, the admin might want to see more information so they can look into more recent crowd levels. So these are the individual inputs based on the users. So there's also a map view for the admin if they want to visualize the hotspots in the area they are at currently, because with a large quantity of data, there might be too many points for the admin to manage. So with this map view, at a glance, they'll be able to see what are the potential hotspots. So previously we've seen that, let's try and find, so over here you can see Brisbane Voucher Street 66. It's marked in orange because it's of a little crowd. So this is one of the ways that the user input data is used to help the admin visualize where are the high crowds at. So going back to the user inputs, remember I mentioned previously that there is some audio and accelerometer data that is also being collected as well. So you can see that over here we have some various points. So basically when the user is running the application, we have based on the audio and accelerometer data, we can detect when a user might be in an area that is crowded. So this is also in conjunction with the location data. So basically, let's say I'm currently at Coast West End and maybe I'm walking towards Messina over here. So as I'm walking, maybe maybe it's a Friday night and there's a lot of crowd. So there might be a lot of noise that is detected by my audio sensor. And because of that, I might also be having to dodge around. There's a lot of gyroscopic movement of my phone because I need to move around other people. So these are two of the sensors that we are going to use here, actually three. So the three sensors is the gyroscopic data, accelerometer data, and the audio data. So to simulate that over here, I will just set a new location here. So set location. And over here in the virtual sensor, I will just try and simulate some gyroscopic movement. So on the admin application, we should see some data based on what was collected from the user. So if we recall, the location where the movement was detected was near Gelato Messina. So if we go to the admin application, yep, so over here, if I zoom in to where the Gelato Messina was, you see we have a new set of data over here that shows little crowd and the latitude and longitude. So because this is just one data input from that movement that we detected just now from the user application, so there might not be any history here. But if let's say there's another user, we could imagine that another user is here, and maybe they also have some movement over here. So because this is a minimum viable product, so in reality, if we have a fork device, hopefully there will be lesser latency. So in this case, you can see that there's another marker there that shows another user, the sensor data collected from the three different sensors and how it could contribute to a little crowd at the area. So ideally, these two data points could be aggregated to more accurately represent whether this area might be more crowded or less crowded based on the different data collected from the user's mobile device.
My name's Leanna, and I'll be talking through the IoT structure for our application. So in our device here, the mobile application device collects user input, sound, accelerometer, and gyroscope data. Beacons collect data on the number of users within their range and transmit this to the application devices and gateways using the alt beacon protocol. In our gateway tier, gateways are distributed by general location and aggregate data from mobile application devices and beacons. They send this aggregated data to the FOG device using the constrained application protocol, which is chosen for its simplicity and low latency. In our data tier, data is unstructured to allow flexibility of data collected. To further reduce latency in the future, some components of data storage can be migrated to structured data. In our analytics tier, the location-based analysis is done through processing the number of devices detected around the beacons. And in our application tier, users receive real-time updates on crowd levels during navigation. They can view a map displaying areas of high crowd for decision-making. In our admin's view, admins will receive real-time updates on crowd levels in managed locations or events, and urgent spikes in crowd levels trigger alerts for immediate attention. I'll now be going through our IoT structure diagram. So in our IoT layer, we have beacons and we have our user's mobile device. So when a mobile device is in range of a beacon, the beacon will send a Bluetooth signal to the mobile device. Then the user will receive a notification where they can rate the crowd level. So that's either little crowd, medium crowd, or high crowd. And this crowd level, determined from the user input, as well as the location and the beacon ID, will be sent through to the FOG device. Furthermore, the user's mobile device collects sensor data such as accelerometer, gyroscope, and the noise level, and that will be put through an algorithm to estimate the crowd density. This estimated crowd density from the sensors, as well as the user's location, will be sent through to the FOG device. On top of all of that, every single beacon collects the number of devices in that beacon's range, and they send that number through to the FOG device. The FOG device will then aggregate the updated data by the location, getting the average crowd level of each of the areas and combining the user input, the sensor data, and the beacon numbers. That aggregated data will be sent through to the MongoDB Atlas Cloud database. And then the estimated crowd level, combining all of that data, will be sent through to the user in the location that they are at. Furthermore, that data will be sent through to the admin, and it will be displayed on the heat map for each location, as well as a risk level of each location that is being monitored. I'll now be going through some UML diagrams. So in scenario 1, a user is finding a less crowded route on foot to get to a destination during the 2032 Olympics. So a FootMaps user selects a destination, and the monitoring service will send the route data through to the cloud database. The database will then send the crowd levels data for each of those routes back to the monitoring service, and then that information on the routes is sent through to the user. The user then will select a route, and then once they are on that route, when the user passes by a location beacon sensor, the beacon will emit a beacon signal. And once that signal is detected by the user, they will receive a notification, and then they can input the crowd level. So that's little crowd, medium crowd, or high crowd, and that's sent through to the monitoring service. And then that processed crowd data is sent through to the database. In scenario 2, a system monitors location in an assigned area, checking the crowd levels and past history to ensure safety. So this is on our admin view of our application. So the monitoring service will periodically query the cloud database for the latest area data, and then that crowd data is sent back to the monitoring service. The monitoring service will then aggregate that data and perform a crowd level risk check. And then an alert of dangerous crowd level will be sent back through to the admin, and the admin will then alert authorities. And then while that's happening, the monitoring service will continue monitoring for new area data. In scenario 3, an admin manually views active locations, checking the crowd levels. So our FootMaps admin will request the latest crowd levels from the monitoring service, which will then be queried to the cloud database. The latest crowd data will then be sent back through to the monitoring service, and the crowd location data will be aggregated and then displaying the safety status of each location back through to the admin. The admin is then able to alert authorities of any danger. Finally, in scenario 4 of our application, a user walks with the application open and their sensor data is sent through an algorithm to determine the estimated crowd density of that area. So when our regular user has their application open and their location is changed, the sensor service will obtain the latitude and longitude of that user, as well as the sensor data. That sensor data, so that's the sound, the accelerometer, and the gyroscope data, that will be sent through to the crowd density estimation class, which will then have an algorithm performed on it, and it will determine a crowd density. That crowd density is then sent back to the sensor service, and the sensor service will then send the crowd density, the latitude, the longitude, and the date and time back through to the cloud database. The cloud database will then send the estimated crowd density of the area back through to the user, as well as every user and admin.
Thank you. So to begin on security measures, FootMaps integrates multiple sensors into its various features to provide a good user experience. Each of these sensors enhance the functionality of the application, but also introduce a list of potential security vulnerabilities that need to be addressed. Our risk analysis assessed various security threats by considering their consequence, severity, risk level, and proposes a specific control to mitigate each risk. The use of a risk analysis allows for easier identification of the risks associated to our application and mitigation planning against them. With geolocation, this sensor allows for real-time tracking of a user's position and is the key component of our navigation feature. However, it also presents a considerable security risk to the application. A few examples of threats involving geolocation are unauthorized access of geolocation data, potentially resulting in exploitation or a privacy breach. It was noted as high severity and a medium level of risk. A possible control for this threat is to ensure users provide consent for their location sharing and to encrypt the data during storage and transmission. Another risk considered is inaccurate geolocation data collected, possibly resulting in the user retrieving incorrect location and route details. This is considered low severity and level of risk, with a mitigation strategy involving data validation and location accuracy checks that ensure the user's location is up to date when using the application. With the beacon sensor, used for proximity detection within the app to trigger the user for their rating of a location's crowd level, it is implemented for use throughout the app navigation and across the administrative dashboard to better track crowd levels based on the user experience. An example of a threat from our risk analysis for using the beacon is in the event of physical damage to the beacon sensor, the user is unable to emit the signal for crowd data collection. This was considered medium severity and a medium risk. Our control for reducing risk is placing the beacon sensors within secure locations to prevent potential damage from harmful actors or environmental factors. For the accelerometer, it is a crucial sensor for detecting a user's movement and allows us to introduce another factor to take into consideration for crowd levels. An example of a threat from our risk analysis is the manipulation of accelerometer data. This would lead to inaccurate crowd density data and could lead to false safety concerns. It was considered medium severity and a low risk. Our control to reduce the risk is for accelerometer data validation and a system in place to identify data anomalies. The microphone usage within the app allows for monitoring of a user's surroundings, taking into account the noise levels that may come from a large crowd. This introduces additional security risks such as if a malicious actor gained access to the user's microphone, it'd be a violation of the user's privacy and cause potential legal consequences. This is considered high severity and a high level of risk. A control that can be utilized to reduce the risk is to only enable the microphone during usage of the application and with explicit permission from the user so that they are aware. Across all these sensors, data privacy remains an important concern. The collection of data that could possibly identify the user increases the safety and property risk of users. To ensure the users are protected, data privatization is required through anonymizing data collected. So when a user inputs the crowd levels for an area, only the input data and beacon location will be uploaded to the cloud, omitting any user-specific information. By implementing our proposed security measures, we would minimize risks and ensure that users can rely on FootMaps to safely and securely manage their data. Thank you.